Okay. So our next speaker, Devi Parikh, is from Georgia Tech, and she's going to talk to us about words, pictures, and common sense. It's rare to get a talk on common sense. So yes, please.
All right. Thank you for the introduction. So my background is in computer vision, and in particular in semantic image understanding. And so traditionally, we've been interested in problems where you take an image like this and you want to recognize all the objects, segment those objects out, figure out, is this an indoor scene, is it an outdoor scene, is this a college campus, is it a beach, where are all the people, what are they doing, how are they interacting with each other, and things like that, right? But more recently, there's been more and more interest in taking this understanding of the image and converting it into natural language and communicating it to humans, right? So be it tasks like describing this image in one sentence, or maybe tell a short story about this image, or if I ask you a natural language question about this image, have an agent that can answer it, or someday even have an agent that can hold a natural language dialogue with a human grounded in this image, right? And so I think the space of understanding images, converting this understanding to natural language and communicating it to humans in a natural way is an exciting space. And so one reason for this is, in addition to sort of it posing interesting challenges in AI research, it's also interesting from an application standpoint, right? And the reason for that is visual data, images, videos are everywhere, and words are how we communicate, right? So if we have mechanisms to link these two, it can lead to many different applications, right? So for example, if you're trying to interact with, organize, navigate through these typically large quantities of unstructured visual data, then natural language is a very convenient way of doing it, right? It's a very natural way of doing it. A lot of the information on the web is inherently multimodal. There are images and text at the sort of that coexist. And so if you have a way of linking those, then you can extract more information about our world and take advantage of that for other applications. If you consider scenarios where you're thinking of visually impaired users, where the users don't have access to the visual data, but they do have access to the language, and so if you have a way of connecting those two, then through the language, some aspects of this visual data are now accessible to users who wouldn't have access to it otherwise. Right? So it's not too far off to sort of envision a scenario where if someone puts up a picture on social media, you start off with the system describing this image in a sentence, and then if the user is interested in more information, they can ask follow-up questions that the system can then respond to, and they can keep going, right? Also in situations where the user might not be biologically impaired, but sort of situationally impaired, in the sense that there's just too much visual data for someone to sit down and process and think through. Then, for example, analysts trying to make decisions based on surveillance data, again, it's useful if you can use natural language to extract the relevant information that you care about and have a system respond appropriately, right? So did anyone enter this room last week? Yes, 127 instances logged on camera. Were any of them carrying a backpack? And so on, right? And this is also relevant in scenarios where there's an agent in the world trying to take action, but is limited through, let's say, the bandwidth of the network. So you can't send through all the visual data that you're perceiving to a teleoperator for them to make the decisions for you, right? So in this case, again, there could be a person that's remote that's asking relevant questions. Is there smoke in any room around you? Yes, in one room. Go there and look for people, right? So sort of having this conversation for the purpose of an agent taking certain actions in the real world. Right? So in all these situations, it's useful to connect the visual data to language. Right? And so one, as you can see from these few examples that I showed you, one concrete task that nicely falls at this intersection is visually grounded dialogue. Right? And so a couple of years ago, we took sort of one first step in this direction where we said, let's not think about the back and forth and having an actual conversation. Let's just think of sort of a one snapshot scenario where you have an image and you have one question about it, and can we build agents that can answer this question for us, right? And so these questions can be literally any question about this image, right? It can be things like what color are her eyes, that involves detecting small regions in the image and classifying some attribute about it. What is the mustache made of, sort of involves recognizing objects out of context. How many slices of pizza are there? You need the agent to be able to count. Is this a vegetarian pizza, right? You need the system to be able to have access to external information that tells you that if you see meat in the image, the pizza is probably not vegetarian. Social context, is this person expecting company? Scene level attributes, does it appear to be rainy? And so on, right? So literally any question about the image. that this would have to deal with. And so as a first step in this direction to try and sort of make progress and benchmark progress, not just for the lab, for the community as a whole, we collected this large data set that had over 250,000 images that had sort of images that look like this. These are just a random sampling of images from the data set. And we also had 50,000 images made from these clip art objects, these cartoon scenes. And what's nice about these is that the low-level semantic understanding of where the objects are and where they're present, what these objects are, all of that is trivial to solve, right? So you can start off from that as your signal and focus on the higher-level reasoning to answer questions about images. And so for each one of these images, we had people ask 3 questions for every image. So that gave us over 750,000 questions. We collected these questions on Amazon Mechanical Turk, where we showed them an image, and we asked them to ask a question that they think would stump a smart robot. So that was sort of our prompt to them to try and get them to ask somewhat interesting questions. And then each of these questions for every image has been answered by at least 10 people, and so that gives us 10 million answers in this data set. And so all in all put together, this would have taken sort of one person 20 years of a full-time job to get all of this annotated. But on Mechanical Turk, it was obviously much faster. And so when you collect data at this scale, you get sort of entertaining comments from these Turkers, right? So these are people doing this work on Mechanical Turk, getting paid in response for it. And here are a few ones that I find interesting. So one worker had to say, beware also the lasting effects of doing too many. For hours after the fact, you will not be able to look at any photo without automatically generating a mundane question about it. If I were in possession of state secrets, they could be immediately tortured out of me with the threat of being shown images of skateboards, trains, Indian food, and beep giraffes. So this data set had a lot of giraffes and skateboards and trains and Indian food. Please, I will tell you everything, just no more giraffes. But out of this, the more relevant thing that came out was this data set that has many interesting questions. Here's just a snapshot to give you a sense for the kinds of things people ask. So these are the first few words with which a question starts. So there are some questions like is, the, is this, is there, that all have sort of binary, mostly yes or no answers. Questions like how many, obviously you have a lot of number answers. What color, you have a lot of color answers. Which, you have sort of left and right as answers. But then there are other questions like what is, what kind, what are, that just have a sort of wide variety of answers that people give, right? And so what you're trying to do is train a machine that can do this, right? Given these questions about images, answer the question. So I'm not going to be going into details of any models, but just to give you a sense for where state of the art stands. So on this data set, human accuracy is at 83%. And the reason it's not 100% is because these are open-ended questions and people answer them in open-ended ways. So 2 people might not give you the identical answer back, right? They might use synonyms. In some cases, there might be some ambiguity. So there would be disagreement at the level of string matching in the answers. So human performance is 83%. One of the first models that we introduced about, I guess, a year and a half ago started off at 54%. And state of the art today is at 68% on this task, right? And in fact, all of the models use deep neural networks in different ways for the image and for the language and for reasoning and so on. Right? So just to give you a sense for what this looks like, I'll show you a demo of one of our earlier models. This isn't even a state-of-the-art model. And so we're hosting this demo on Cloud CV. This is publicly available for anyone to try. So you can upload any image, and you can ask whatever question you want about it, right? So what is in this image? It says food. What kind of food is it? It says sandwich. How many sandwiches are there? 2. What are the sandwiches on? Plate. What color is the plate? White. Is there wine in the image? Yes. What kind of wine is it? Red, and so on, right? So you can ask, so this is a bit of a cherry-picked example, right? I'm up here giving the demo, but it's publicly available, so you're welcome to try and break it. But this is just to give you a sense for sort of the kinds of things you can ask and the kinds of things these models can answer reasonably well. Right? And so visual question answering has gained quite a bit of traction. There's been a lot of papers that came out on this topic in the last couple of years. Interest from academia, industry, startups. Our data set is quite popular. We've released code for several models that can do visual question answering, so it's a nice step for someone to get started on this. We organized a challenge at one of the top-tier conferences in computer vision last year in the summer. There were 30 teams from around the world that participated, and so it's been an exciting space, right? And so this is great. I showed you a bunch of things that this model can do, but there's still a lot that it can't, right? So for example, if you take this image, and if you were to ask one of these models how many vegetarian slices are left in the pizza box, I'd be very surprised if they got it right. And even if they got it right, it would probably be by fluke and not for the right reasons, whatever right reasons means, right? But not in a way that we would think is interpretable. And the reason for this is several things. So one thing that's interesting is these models can't really count very well today, which might be surprising given the state of the art in deep learning. And so my lab has been focusing specifically on this counting problem to see if we can make progress on that. These models don't leverage external knowledge bases. So for example, realizing that vegetarian means the absence of meat, these models right now are not doing a good job of that at all. These models can't really reason. So realizing that left in the pizza box means stuff that is in the pizza box as opposed to outside of it. Or if I were to ask a question, what is the color of the t-shirt of the kid that is to the right of the child in the black t-shirt? Sort of if you have these complex spatial reasoning questions, these models can't deal with them very well at all. They don't leverage compositionality. So if the model has seen vegetarian sandwiches, vegetarian pasta during training, and it has also seen pizza slices during training, but if it hasn't seen the concept of vegetarian pizza during training, it probably won't do a very good job of generalizing at test time. So they're not good at leveraging sort of these compositional properties of language. And they lack consistency, right? If I were to ask a question, how many slices of pizza are left in the box, it might say 3. And then if I say how many vegetarian slices of pizza are left in the box, it might say 4. And it won't realize that if there are only 3 slices to begin with, how can 4 of them be vegetarian, right? And so that's where things stand today. And one reason for sort of lack of this consistency is because it's treating every question independently, right? Every new question is thought of as a new input, and there isn't sort of continuous modeling that it's doing. Right? And so that's where things stand on visual question answering. More recently, we've pushed on sort of going towards that goal that I mentioned earlier of having an actual dialogue with an agent. And so what we've done recently is we've collected this data set where we pair 2 Mechanical Turk workers up with each other live, so they're chatting with each other. One of them is a questioner who does not see the image. They just see a caption of the image, and they're trying to find out more about this image, and so they're asking questions. And the other end is an answerer who is looking at that image and can answer whatever questions the questioner is asking, right? And so this is an example of their interface. Again, this side is the questioner. They don't see the image. They just see a caption. And they're asked to ask questions that will help them imagine the scene better, right? And so they're asking questions, and they're paired sort of live with this other worker who is seeing the image and the original caption, and they're answering questions, and they're going back and forth and having this dialogue. Right? And they do this for 10 rounds, right? So for every image, we have a dialogue that's 10 rounds long. So we've collected this data so far for 100,000 images. We're still in the process of finishing this. We're continuing on to finish it on one of the standard data sets. 1 dialogue per image, 2 people chatting live, and 10 rounds of interaction per person, right? And so once we have this data, we can start training models that try and leverage this history of the conversation to answer questions. And so sort of we've built this. This is not live yet. It's not publicly available, but this is an actual system that's where you can start by uploading an image. It starts off with a caption, and then you can ask follow-up questions, right? So what is this moped? Where is this on street? How is the weather? Cloudy sky, looks clear, right? So you see there's a bit of a funny thing there. You're saying cloudy sky, but that looks clear. You'd probably say it's a clear sky, but there are some clouds, right? So it doesn't get that right. Are there humans? No, I don't see any people. So you can tell that the language is more conversational now. You're getting longer answers than I showed you earlier on the visual question answering demo. What is the road made of? Asphalt. How many bikes are there? I can see 4. What else is there? I see 2 street signs, and there is a sign that says Unk. So for any of you who've trained models using natural language, your models typically have a finite vocabulary, and so they have this special token called unknown token that tries to cover everything else, and that's what this Unk is. So this is to show you this is an actual system that's spitting this out. It's not some human at the other end that's responding, right? So this is just to give you a sense for where things stand, right? These aren't super accurate. It's just sort of a first stab at this. But this is what we can do. And so this is reminiscent of this application I showed you earlier, where you could imagine using this on social media, for example. Right? So sort of pushing this even further more towards this having a conversation for the purpose of having an agent take some action in the real world. Something that we're thinking about more recently, very recently, in fact, we haven't gotten started on it, is trying to, so we're not sort of, I'm not a roboticist, I don't work with physical robots moving around in the world, but I think this idea of dialogue-driven action is still interesting. And so what we're considering is this sort of closed world where an agent, not a physical robot in the 3D world, but an agent can take a finite set of actions and has access to sort of a finite world, right? So there are these objects, and it can place it at different locations. It can flip them left and right. It can make them 3 different sizes. And this agent can sort of, these are the actions it can take, right? And so what we're trying to see if we can create a scenario where there's one person that plays the role of a describer, right? And so this describer sees a reference image, and they are trying to have a conversation with an agent, which during training would be another person, but in reality would be a bot, who does not see this image, but they're having a conversation to get the bot to create this image in that interface that I just showed you. Right? So the describer sees this reference image. The actor, which is the agent, does not see this image. That agent has access to that world, that interface that I showed you, where it can take actions and move and drag and drop objects. And the describer is having a conversation with the actor to get the actor to create the same scene that the describer is looking at. Right? So here's one example. This was just me and my colleague trying this out. This is one conversation that it could look like, right? So the describer sees this image, and I, as the describer is trying to get me to create the scene. And so I start by saying what is going on in the image overall. The describer says 2 people are playing. I know that these 2 people in this world have the name Mike and Jenny. So I say, is Mike to Jenny's left? No, on the right. Right? So with this information, I already sort of create on my canvas, I'll drag and drop objects that respect the spatial configuration. The describer then tells me there is an airplane, so I go ahead and place an airplane. What else is there? Sun is on the top right corner, and a tree on the right side with fruits. And then I have a clarifying question to figure out which way the plane is supposed to be facing. Is the plane facing the sun? They say yes. And so I go ahead and update my scene with these added objects, making sure the plane is in fact facing the right direction, and so on, right? So this conversation can continue where I am trying to create a scene that matches what the describer is seeing, even though I can't see it, right? And so if you have data of this form, you can imagine building bots that can now have this conversation with you, where based on the conversation, they are taking actions in the world. All right. And so one last piece that I want to talk about is relating. So all of this is exciting from sort of words and pictures and what we can do there. But one component that's missing in a lot of these systems is common sense, and that's loosely defined. So I will not try to define it, but I'll give you some examples of what I mean by that. So now we have these machines that are really good at doing things like this, right? Given an image, they can convincingly describe it as man in blue wetsuit is surfing on wave, or a group of young people playing a game of frisbee, or a car is parked in the middle of nowhere, a pot of broccoli on a stove, right? So these literal descriptions, these models are fairly good at. But if you think about what it would take to describe a scene like this, right? A reasonable description is a man is rescued from his truck that is hanging dangerously from a bridge. Right? And if you think about what it would take to utter these words, rescued and dangerous, right? It's not just literal information that's in the pixels. You need to have a sense for what must have happened in the scene before this, what might happen after, and use sort of external knowledge, external common sense to realize that you should use words like rescue and dangerous, right? And that's something that's lacking, right? And so if you think about, well, where can we learn this common sense, right? So one response that you often get is, well, you can use all the text on the web to learn it, right? And that makes sense. That can get you a long way. But text is known to have reporting bias, right? Text is written by humans to communicate with other humans, and we like talking about interesting things. We don't like talking about mundane, boring, common things. And those common things is usually what you're after when you're trying to learn common sense. And so text can have issues with that, right? And so let me give you an example of that. So this is how often these different phenomena are mentioned in text with respect to people, right? And if you were to think that the number of mentions or the frequency of mentions is a proxy for the frequency of occurrence of these phenomena in the world, then you will have some issues with that, right? So for example, if you look at these statistics right here, we would end up concluding that people inhale 6 times as often as they exhale. And maybe what's more disturbing is that we would conclude that people get murdered 17 times as often as they exhale, right? And that's just not the case. It's just that it's more interesting to talk about murder than it is to exhale. Here's another example, how often different body parts get mentioned. And we would end up concluding that people have heads 1,100 times as often as they have gallbladders. But again, that's not the case. We just don't like talking about gallbladders, right? And so one sort of our response to this, as maybe perhaps with a bias from a computer vision standpoint, is that, well, how about instead of trying to learn it from text, we just try and learn it from the visual world around us, right? Perhaps there's less of a reporting bias there. And there is a lot of structure, right? If I show you this image and I ask you to describe it, you might say that this is a picture of 2 professors conversing in front of a blackboard, right? And if I change now one subtle thing about it, your description will change, right? Now you'll say that these are 2 professors standing in front of a blackboard. Right? So how do we get machines to learn that the subtle difference in the gaze of 2 people can be the difference between them talking to each other versus just standing near each other, right? So there are some challenges in trying to do this, right? One challenge is we usually lack this visual density. We don't have access to multiple images with subtle changes in them where we know how the meaning changed, right? And moreover, even if we had such data, getting every single attribute of every person, of every object, including their gaze annotated, is going to be very expensive, right? And so you might say, well, you're a computer vision researcher, why do you need it annotated? Just go ahead and detect it automatically, right? But computer vision isn't quite there yet, right? We can do a lot more than we could 10 years ago, but I don't think we're still at a point where we can list every single attribute of every single thing that's happening in the scene. And so this leads to sort of a chicken and egg problem, right? On one hand, I'm saying I want to learn common sense so that I can make image understanding better. And then I find myself saying that, well, if you just solved computer vision, you would be able to learn common sense from the visual data around you, right? And so what we wondered was if there's a way to sort of break out of this. And the way we did that was to question whether we really even need photorealism in the first place if what you're interested in doing is learning common sense, right? Because the common sense is not sort of in the RGB pixel values, it's in the semantics of the scene. So if we had visual data that is semantically rich, but need not be photorealistic, maybe we'll be able to learn something from those, right? And so with that thought, we introduced these 2 characters that I referred to earlier, Mike and Jenny. And they had this world of different clip art objects, indoor, outdoor scenes. Mike and Jenny can have different poses, different expressions. And through the interface that I showed you earlier, we can do fun things. I can now hand you that interface and I can give you a sentence that says, Mike fights off a bear by giving him a hot dog while Jenny runs away. And I can ask each one of you in this room to create a scene that depicts this. And every single one of you will probably create a different scene that all still have the same meaning, right? The objects that are in these images might be different. There may or may not be trees, might be different kinds of trees, may or may not be sun and clouds and so on. They will all have Mike, they will all have Jenny, they will all have Mike facing the bear, holding a hot dog, and Jenny running off in the opposite direction, right? And so this level of visual density you would just not be able to do with real images, right? How would you find 6, 10, 50, 100 real images that are all different in terms of the pixels, but have the same underlying meaning? And so this is something that you can do if you're in this clip art world, right? And so coming back to common sense, we wanted to see if you can use this abstract visual world to learn common sense knowledge, right? And so, for example, one task might be that it's a fill-in-the-blank task. Mike is having lunch when he sees a bear, and then what happens? Does he order pizza? Does he hug the bear? Bears are mammals. Mike tries to hide, right? I think from common sense, we would all know that D is the likely response. Another task might be I give you 2 descriptions, and your task is to figure out if this could be describing the same scene or not, right? And our sort of key idea in this was that in trying to solve this problem, right, the input to the problem is just text, whether it's fill in the blanks or paraphrasing. Instead of just reasoning about the text, our thought was that if you imagined the scene behind the text and reasoned about the scene as well as the text, you might be able to do a better job, right? And the intuition behind this is the following. If this was the task, you need to figure out if these 2 descriptions are describing the same scene. Jenny was going to throw her pie at Mike, and Jenny is very angry. Jenny's holding a pie. Now, if you were to try and use text, you would have to reason about the fact that if people are angry, they tend to throw things, and if you want to throw something, you have to be holding it, right? But our thought was that instead, if you just imagine someone throwing something, you will imagine them holding it. And so instead of having to go through this multi-hop reasoning in text, in this visual domain, it might be much easier to tell that these 2 descriptions could be describing the same scene, right? And so that's exactly what we do. For each one of these options, we plug it in. We want to generate a scene, do this for all 4 options. Again, the idea is that these scenes don't need to be photorealistic. The RGB values don't matter. It's just the semantics that matter. And so we generate these scenes in this abstract board. So we have a way of taking text and automatically generating a clip art image to go with it. And then we can reason about the image and the text both to figure out which option is more likely. And we find that this gives you improvements in performance over just reasoning over the text alone. Right? One other fun thing we've been doing that's related to common sense is detecting humor. So we've been asking people to create funny scenes for us and explain to us why they think this is funny, because sometimes it's hard to get the sense of humor on Amazon Mechanical Turk. So the terrified woman's home is being invaded by mice as the cat sleeps. The man is about to trip on his child's car and spill wine on his wife. And so we're trying to use this to see if we can get machines to detect humor and even create humor in this abstract world. So that's a bit of a tangent, but with that, I'll summarize. So I talked mostly about visual dialogue. I think it's an interesting and exciting space at the intersection of words, pictures, and common sense. It has several applications, and one thing to keep in mind is if you think about all the chatbots, Siri, Alexa, and so on that you have access to, most, if not all of them are blind. They don't deal with visual data, so I think there's a lot of scope for applications there. And there's a lot of exciting AI research to be done, right? On the computer vision side, language understanding, attention mechanisms to figure out which parts of the image are even relevant, complex reasoning, using external knowledge, common sense, and finally even pushing sort of this visual dialogue towards action and manipulation in some world. And with that, I'll stop. Thank you.